Okay, so welcome to the last discussion of MA 175. I am glad you are glad. Let me give you a quick overview of what we did in the morning. So if you go back and watch the video, you will see that first I discussed a question based on a second order system. We went ahead and found out its transfer function. We found out how to classify a second order system as underdamped, critically damped, or overdamped. What are the eigenvalues and eigenvectors of the second order ODE? How do you relate the stability both from the transfer function side as well as the state space side? And then if you have a second order ODE, then you should have the formula for peak time, percentage overshoot, and settling time. And remember that peak time and percentage overshoot are only defined for underdamped systems. They are not defined for critically damped and overdamped. Why? Because critically damped and overdamped systems do not overshoot. And then I went on to solve a short question on short period dynamics for the Navion aircraft, where we basically constructed the 2x2 reduced order model approximation based on the total equations that we had. Then we went ahead and looked at its characteristic polynomial, what would be the roots. Yep.
I have a question. So for homework 1, since it has a graph similar to the
Homework 5, yeah. Yeah.
Question 1.
Yeah.
Are we just supposed to calculate like zeta and omega n using like the settling time?
Yep.
Okay.
Because you don't need the settling time. You only need the expressions for percentage overshoot and peak time. And if you want an even more better explanation, then go and watch the Office Hours 10 video, the last video that's posted in the MA 175 playlist, because I haven't posted after that. So today I'll post 2 more, and then I'll also post the audio corrected version later. I'll also post the muted video. If you can follow, fine, but give me Saturday and Sunday and I can post in some more examples. But yeah, there I have taken up in depth like how do you use the figure, and don't hesitate to use the figure in an MA 175 exam or course. Okay, figures are very important. You can get a lot of information. Okay, so let's move on. So in the second part today, so the second question, or question 3, is on long period dynamics. So long period or phugoid mode, right? So the phugoid mode represents a trade-off between what? Kinetic and potential energy. Why? Because your aircraft is literally doing this. So when you go down, you gain kinetic energy, but then you need to settle down, and then that kinetic energy is converted into potential energy, back to kinetic, back to potential. Using the long period approximation, which assumes that alpha is approximately 0, construct the 2x2 state matrix A phugoid or A long period and construct the frequency. So the first part of the question 3.1, you can say it is asking us to find out the state matrix, the natural frequency, and the damping ratio for long period. Okay, so what are you going to do? You are going to go and look into your cheat sheet. It is always better to keep the 4x4 model. Remember that in long period dynamics, our approximation is alpha 0. Okay, so if you go ahead and plug in and neglect alpha, you will simply get ALP as XU negative G negative ZU divided by U0 and 0. Also remember that sometimes you might be given stability derivatives such as MQ and not M, or let's say you will be given like for example NV, but you require N beta. Okay, so is it a problem?
You have to
Convert it. Okay, be very cautious. alpha is equals to u over u naught, beta is equals to v over
W over U naught.
oh yeah, sorry, w over u naught, and beta is equals to v over u naught. Okay, is that clear to everyone? Now once I have the a long period, you can look, yeah.
So to go from n beta to nv, do you
Yeah, so
divide by u naught or?
think, what is n beta? Del n by del beta. What is n v? Del n by del v.
Mhm.
What is v? V is beta times u naught. So del n by del v becomes del n by del b times u naught. So you pull out u naught, 1 over u naught times del n by del beta. So you divide by 1 over u naught. Okay. You can also like remember it like n divided by velocity, n divided by radians. How do you put them equal? Radian is unitless. So n has to be divided by a velocity to make both the constants equal. Okay. And I know if you don't breathe calmly on Tuesday, you will make this mistake. So breathe calmly. I'm not joking. Now, if you go and I have provided the numbers, but just for the sake of quickly, this is a discussion. I'm not plugging in the arithmetic, but you will get all the numbers, all the answers in a different sheet. The solution will not be provided. I'm sorry, I don't have the time to type up the entire solution. So come back to the video and watch it. So if you go ahead and plug in the values that are there in the question, you will find out that it comes out to be negative 0.045, negative 32.17, 0.0021 and a 0. So what is left to find out? The natural frequency and zeta. Again, the same thing that we did in the short period in the morning as well. When you will watch, you go ahead and construct the characteristic equation of your system matrix and put it equal to 0. When you do this, you are going to get s square plus 0.045 s plus 0.0676 equals 0, which would give you. Now, how will you find out omega n long period and zeta long period? Compare it to the equation of any second order equation, second order system. And from here, you know that omega n square long period is 0.0676. Am I done? Okay. And because a lot of you like one severe feedback that I gave about the midterm in the morning, which I hope I do not see it again, is midterm question 1. I think 80% of the class got it right, but still only 3 people got to the correct answer because most of you messed up in the degree to radian calculation. So don't do that, okay? I mean, I'm bound to take away half and half there. And you realize that in the final, you will have questions like these, where you find out the natural frequency, find out the damping ratio, then go on and get into the desired damping ratio, desired frequency, design a closed loop controller. So if you make a mistake in the start, it's going to keep piling over later on. And then you have 2 zeta long period, omega n long period equals 0.045 per second. If you I think, yeah, what's the values that we get? So here, if you solve them, you get omega natural as 0.26 radians per second, and you get zeta long period as roughly 0.087. So what do you think? Is this an underdamped mode, critically damped mode, or overdamped mode? Yep. Yes. Why? Yep. Exactly. So zeta is less than 1, which means it's underdamped. If it was exactly equal to 1, it would be critically damped. If zeta were greater than 1, it would be overdamped. Now, just based on the factor that this is an overdamped, underdamped system, can you predict the graph of its response if it were given a steady state input, let's say? What would be the response? Yeah.
Like overshoot.
Yep.
Possibly.
Excellent. So you will see overshoot, but because the damping is very bad, it's very low, it will keep going for a long time. For a long time. Okay. Like if I try to compute the settling time, TS is 4 zeta omega natural, right? So let's try to compute that. 4 over roughly 0.09 times 0.26 second. So I could like approximate this as I could turn this as into 10 to the power 2, this becomes 26, into 10 to the power 4, this becomes 9. So, and I could approximate this. So roughly you can see that it's roughly 10 and it's 40. So 200. So it's about 100 seconds, about less than or more than 100 seconds probably. Okay. Which is a long time. It's like 2 minutes, 3 minutes. Like if you are in an aircraft and a turbulence hits, you keep doing like this for 2 minutes. Okay. I feel like vomiting in 30 seconds. So this is not the desired characteristics. So definitely the next question or next part of the question is going to be, why am I asking this question, that what is the next part of the question going to be, so that you are prepared, you don't get surprised that, oh, the question is asking what, the damping is poor, I am going to have a bad flying quality experience.
Oh.
So what am I going to do next? No, not you. What am I going to do next? Feedback control. Okay. Also, just a short note that if you do the short period approximation and go ahead and find out the natural frequency, then recall that the natural frequency roughly comes out to be root over 2 g over u naught. Okay. For this question, it's 176 feet per second, and g is going to be like, you have to convert it into SI units, 9.81. If you compute the omega n here and the omega n for the 4x4 system, they are going to be pretty off, because the long period dynamics is not an accurate representation of the full 4x4 longitudinal dynamics. Keep this in mind. Remember that the long period and short period are coupled. Short period is the dominant one. Long period is not the dominant one. Okay. And then we have the fact that long period does not approximate it well. So you will find out that the natural frequency you get from the reduced order model of the long period is not as accurate as the natural frequency that you get from the 4x4 model. Okay. And this, yes.
How did you get that expression
With omega n?
Grad 2.
The 4 over zeta omega n? Yeah, so that's like more of a control theory question. I mean, I can take that up personally, but like, are you asking for its derivation?
Oh, or like, should we just write that down?
Yeah, this is a formula that you can straight away use. So this is also called also to be more specific, this is called the 2% criterion. 2% criterion as in, like, let's say what happens is actually these oscillations keep happening for a very long time. So if you go ahead and look very closely, what's going to happen, so this is your steady state value, and then the 2% of your steady state value is going to be something like this. So the first time that your response enters the 2% bar and never leaves it is called the settling time, and you can derive it explicitly. You can review your control theory notes and you can derive it explicitly. It comes out to be 4 over zeta omega n, and it is independent of the driving frequency. It is only dependent upon zeta, damping ratio, and the natural frequency. Okay. Now it's natural to think that the next thing that we are going to do is design a stability augmentation system, but we don't do it for long period dynamics. Why? I just discussed about it.
Because it would be, it's like inaccurate or, it doesn't, yeah, it's inaccurate.
Yep. So first of all, short period and long period dynamics are coupled. Short period is more dominant. It's much more visible. It has stronger eigenvalues. Its dynamics dominate the long period dynamics. So that is why a reduced order model of a long period mode is not an accurate representation of the entire longitudinal mode. Hence, if you design a controller based on the reduced order model of the long period mode, it's not going to control the complete system or the complete longitudinal dynamics properly. So you will never be asked to design a state feedback control based on the reduced order model of a long period, based on the 2x2 model of the long period longitudinal mode. Okay, and I mean you could make like, so what's happening in the long period mode? If let's say you could control the long period mode, how would you control the long period mode? You would control it by controlling the velocity, forward velocity. I mean, that's the only dominant part here. And to control the forward velocity, there is only one thing you can do. What can you do as a pilot? If I ask you to fly faster.
Increase thrust?
Yeah, I mean, unless, yeah, fly faster. So what are you going to do? You're going to do throttling. Either, so when you are going down, the pilot will try to reduce thrust so that you slow down quickly, and when you are going up and you are losing velocity, the pilot will try to speed it up so that you do this and finally slowly settle down into steady flight. But then the problem is that, you see, in real life, this is your airfoil, the CG is somewhere here, and then the engine nacelle is attached somewhat like this, and then the point where the thrust acts on the aircraft is somewhere here. Now you have huge thrust, small moment arm. What happens when you suddenly increase throttle?
It's gonna wanna pitch.
It's going to pitch up, which is an absolutely undesired thing. And what is pitch up going to do? Is going to affect short period dynamics, because theta is a part of the short period dynamics. So you can see very clearly, conceptually at least, that if you even tried to design a state feedback control for the longitudinal dynamics, the short period dynamics is dominant, and you cannot design a state feedback controller which does not affect the short period dynamics and only affects the long period dynamics.
Wait, theta is long period, right?
Huh?
Theta is long period.
Theta is long period?
Yeah. It's U and theta.
Oh, I meant alpha. Sorry,
Alpha.
alpha.
Oh.
Yeah.
Okay, so is the message you are saying is like so the to use feedback control for the long period is not too realistic.
Yes.
For the reason that there is not a single thing to control that is going to not impact the short period.
Yep. And you can like look at this by looking at the 4 eigenvalues and 4 eigenvectors, which you compute for the longitudinal dynamics. Like, remember that you normalize all of them by delta theta, and you get delta theta as 1, and then you compare the rest of the eigenvalues in comparison to that. So you will see that the short period eigenvalues are larger than the long period eigenvalues.
Larger in magnitude, right?
Yep.
Okay. So like typically if we see a question like regarding longitudinal mode, it's most likely, almost definitely, for feedback control, almost definitely it's going to deal with the short period. Right?
Yes. With the short period, yeah.
Yeah.
Or if we really want to have fun, the entire longitudinal dynamics should be under a state feedback control, and you have like a 4x4 system. But we won't, don't worry. Okay, so moving on, we have 3 more questions, and I think we can, feel free to leave if I cross beyond 4. Okay. So now we are done with long period dynamics. Long period dynamics, total 4x4 system, 4x1 state. We decouple it into We don't decouple it. We use reduced order models for long period, short period, which are 2 by 2. Now, the next 3 questions are based on lateral mode dynamics. Okay. So first of all, we'll look at Dutch roll and yaw damper. Okay. So what does it say? So the Dutch roll was what it is, what happens in Dutch roll. So just to make sure that you understand. So this is what happens in Dutch roll. Okay. If anyone plays Microsoft Flight Simulator, it's very easy to get into a Dutch roll mode with a 787. Okay. And what's the only control input that you can do in Dutch mode? The rudder. Nothing else comes to play. And the problem is that the rudder is usually not that effective. So Dutch roll can take some time to damp out if you don't have feedback control. Okay. And Dutch roll is nasty. You don't want to be in a Dutch roll. Because it's oscillatory, it also causes loss in altitude to some extent, and it's difficult to control. Like the pilot has to keep actively controlling the aircraft in Dutch roll mode. Yes.
For controls, we can't consider the ailerons.
Because then you'll excite the roll mode. Good question. Like the last question is about the coupling of, like, you will see that the spiral and the roll modes are also coupled to some so in lateral mode you really can't decouple anything. In lateral mode, that's why you have a 5 by 5 system, and more or less all the reduced order models are affected by one another. Dutch roll 1 is the most significant. So you go and look at the 5 eigenvalues, you will look at the lambda r, lambda dr, the magnitude of lambda dr. Remember that it has both a real and an imaginary part. Okay. So if you take their magnitude, it's going to be the largest among the spiral, roll and Dutch modes. Okay. So let's, like, using the standard Dutch roll approximation. Where did the question go? Yep. So using the standard Dutch roll approximation involving beta and R, if beta was not given, what else could have been present there? V. Okay. So in the notes, in Professor Taha's notes, the equation is written in terms of V, but in books also equation is written in terms of V. So don't get confused, because in the last in the office hour session also I use beta. I like to remember it as beta and R. Okay. So using the standard Dutch roll approximation involving beta and R, calculate the open loop eigenvalues using the provided lateral derivatives. What are the open loop frequencies and zeta? So 4.1, again, you will go ahead and simply copy down your state matrix for Dutch roll mode, which is going to be y sub v minus 1 n beta nr. All these values will be provided to you, or you would have computed them in a previous question or previous part, or estimated the stability derivative. Excellent. So again, I will not go through. It's the, like, basically I'm doing this again and again so that it gets ingrained in your mind and you never feel confused again. So now you have the state matrix. We want to find zeta and omega n. What are we going to do next? We are going to construct the characteristic polynomial by taking the determinant of Si minus ADR. This will give, yes.
How are n beta and r related to zeta and omega?
So we'll just see here. We'll just see here.
Huh?
We'll just see here. Good question. I'll derive it for you. Yep.
So I saw the one showed up in the lecture note was like I think was like m beta.
YV over U naught.
Yeah.
Yeah, because there it's V. That's what I just said. In the lecture notes, it's the equation is written in V and R. Beta is V over U naught. Show me what you're talking about.
Yeah. So like, yeah, you're right. So it's B, but like, I said like this is prime.
Right. Yeah, prime is because you remember that you have something called IXZ, like these NR and N beta actually have terms which have denominator and numerator, and it has multiplied by IXZ.
Like like you mean the inertia thing?
Yeah, the inertia part. If IXZ is, if the airplane is not symmetric about this plane, then you will have N prime, N beta prime, which is different from NR and N beta. But if the airplane is symmetric about the XZ plane, then N prime beta and N prime are the same as N beta and NR.
Okay, so before the messages they are, so it depends on symmetry, right?
Yep. Actually, I have already provided in the context of the question, like when you go ahead and do this as a question paper, it is given. I have written down that IXZ is 0. So you can assume that you don't need to take. You're correct. Ideally, it is N beta prime and NR prime, but IXZ is 0, so we can assume that. Same. Yep.
That 2x2 matrix and all the other ones like it should go in our cheat sheets, right?
Yeah, definitely. It should. I mean, to be honest, you can write the full 5x5 system and then note down that in Dutch roll mode, these two are absent. In spiral mode, these two are absent. So let's say there are like, let me actually copy that thing for you guys. Oh, my internet won't work here. I'm sorry. But let's say you have like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so on and so forth. And then you see that these two modes or these three things are not involved. So you can construct the 2x2 just by taking these as the new matrix. So you're basically ignoring the effects of other equations which are coupled into the system, right? That's what we do in the short period dynamics. Okay. Now, what's your name? You are Ocean. You? Mason? Yeah, so Mason raised an interesting question which I was not planning on covering, but let me cover again. So, if we hadn't plugged in the values and we wanted to generally derive, which could be a question, theoretical question, how it could be posed, just to keep in mind that if I kept this in the symbolic form and went ahead and constructed the polynomial, it would look something like okay. So now can you relate which stability derivatives contribute to zeta and which stability derivatives contribute to zeta? And it might be asked in the question that since we are changing the damping ratio, which stability derivative do you think is being affected the most? And you have done this somewhere before. Remember that to that in roll mode, not in Dutch roll mode, in the spiral mode, you need to ensure that the product of, I forgot the exact terms, but the product of two stability derivatives has to be greater than the other two stability derivatives, and one of them is yawing and one of them is rolling. I think it's L beta NR should be greater than LR N beta for stability, for dynamic stability. So you need to keep these things in mind, like like zeta and omega n are a natural way or a standard way to analyze any second order system, right? We could be studying Maxwell's equations, we could be doing electromagnetics, I could be doing finance or economics or fashion design. Trust me, math is everywhere in its own form. Okay, and you might be like, okay, so this variable acts as a damping factor for my economic model and this variable acts as an oscillating factor for my economic model, so I can analyze my second order economic model using the second order ODE. You yourself have to make the context here that in flight dynamics, damping is given by this stability derivative and oscillation is given by this stability derivative. Okay, so it's not something very surprising. Why? Because you see, to affect damping, N beta does not absolutely affect damping. N beta affects natural frequency. And actually, when you look at the values, you will see that n beta is the one actually affecting natural frequency. Why? Because n beta is a stability derivative of with respect to an angle. Remember, theta double dot theta double dot minus mq theta minus m theta theta or m alpha theta equals the forcing term. So the spring constant is negative m theta and the damper is negative mq. So any stability derivative which is written with respect to an angular velocity or a velocity is going to act as damping. Any stability derivative which is written with respect to an angle will be a stiffness coefficient. Okay. So now you can go ahead and construct omega n square, find out its value, go ahead and find zeta omega n. So this would be routine, like you would have to do this for anything. This is the first step. So get ready to, like, they should be burned into your brain. Like even if someone like throws water at your face at 3 am and asks that how are you going to get zeta and omega n, you should be able to tell me right then. I wish I could do, but it's not allowed. A yaw damper is proposed to suppress the next part of the question. A yaw damper is proposed to suppress these oscillations because I think, let me just, for the sake of this conversation, let's have some hard numbers. So omega n actually comes out to be 2.14 radians per second. And what else? And yes, zeta comes out to be, I can't recognize my handwriting sometimes. Yeah. This is Dutch roll. Yes. It is 0.237, which means this is underdamped clearly, and definitely don't want underdamped Dutch roll mode, right? It means that the pilot will have to keep operating on the rudder to kill the Dutch roll mode, and it's going to take a long time. Okay. So what do we want? We want a yaw damping system. We want to damp the most dominant mode in Dutch roll mode, which is corresponding to the yaw. I mean, it's both, like beta and R. So you are basically, both the modes are related to yaw angle and yaw velocity. So it is proposed to suppress this using what control input? Delta rudder, and it's going to be state feedback. And I'm explicitly saying that the state feedback is going to be minus KR R. If I hadn't told you, if I had just written in question that use state feedback loop, what would you have done?
Negative KV times V.
Negative KV times V, negative KR times R, or negative K beta times beta, negative KR times R. But here I am telling you that forget about beta. The feedback has, like, I do not have an amplifier or gain or a sensor which is reading beta. The only access I have is to measure R. Okay, and I have an electronic circuit which is measuring R, and then an amplifier is connecting which is providing me the feedback gain. So my control law is only dependent upon R. Excellent. Assuming the rudder control power is also given to you, N delta R is negative 2.0. Determine the KR such that we have a damping ratio of zeta dr equals 0.3. Okay. So what are you going to do next?
Get our matrix, or our A plus.
Yeah, I get the entire steps you are doing, but let me show you a small shortcut which also helps you keep in mind that how not to make mistakes. Okay. So what's happening? I am giving, let's see what's happening. Okay, for a second. I had x1 dot, x2 dot, then I had a1. So let's say a11, a12, a22, oh sorry, a21, a22 times x1, x2. And then I'm saying that, I'm providing minus 0, minus k2, oh sorry, negative 0. B was, actually B would be given like b1, b2 times 0, k2 times same x1 x2, right? So what is going to happen? You are going to get a11, and this would be a minus a11, so this would be 0 b1 k2 0 b2 k2. So which two terms are getting affected? Is a11 getting affected? Is a21 getting affected? Have I done the matrix multiplication correctly? Yeah, I've done the matrix multiplication correctly. Okay. A12 minus b1 k2, a22 minus b2 k2, which means what is getting changed? A constant is getting changed. And what else is getting changed? nr. Okay. Now you see, you will find out that n beta is the dominant term here, which means the natural frequency is not going to change much, but it's going to change. Okay. And what is primarily going to change? Zeta. So you can't just change zeta, you have to shift the natural frequency, will also get affected a little bit, right? Keep that in mind. So if, remember that on Tuesday you will also have a few conceptual questions to answer with multiple choice, right? The professor has informed you of this. So keep these things in mind, that let's say the question asks that, you designed a controller which was supposed to reduce or increase the damping ratio. What do you think happens to the oscillation frequency or the natural frequency? The options might be does not get changed, it increases, it decreases, cannot be commented, but I know that it gets changed. Your answer should be cannot be commented, depends on the case, like depending upon the plus minus sign, it might increase, it might decrease, but it definitely won't remain the same. Okay. Because even in long period and like in both longitudinal and lateral dynamics, you might come up with reduced order models where they might be uncoupled, but if you look at the entire system, you know that longitudinal and lateral are coupled amongst them. I mean, the longitudinal and lateral are separate, but the 4 states in longitudinal and the 5 states in lateral, they are coupled with each other, except one. Which one? Psi in lateral mode. Okay, psi is a completely uncoupled mode in, like it has just one entry 1 in its 5x5 state matrix. Okay, it's just given as psi dot equals psi dot. So psi dot is an uncoupled, or psi is an uncoupled state in the lateral mode dynamics. So you have to remember all of these things. These are small tiny things which will come up in your conceptual questions. Okay, so how am I going to find out the open loop gain? So obviously, like now it's straightforward, you go ahead and do so this is your new A closed loop, and you will have, it will be a function of kr. You will have 4 entries, 2 entries will involve kr, and then you go ahead and construct its characteristic polynomial. Its characteristic polynomial will turn out to contain kr, and then you have to target to get zeta 0.3, that will give you the value of kr. Okay, but what will it show you? That the natural frequency has changed. Your task is to go and see and answer for yourself, does omega n change a lot? And see for yourself what happens. Also try out, what if I wanted to change it to 0.5, 0.75 and even 1? You will see that the natural frequency won't change even at 0.5, at 0.75, but suddenly when you put 1, what's going to happen to the natural frequency? What happens when zeta is 1? It becomes critically damped. There is no oscillation. So actually omega drops down very sharply when you go towards 1. Okay, this comes as a concept of Bode plots. If you recall from, if anyone has taken a control theory lecture before, then if you look at the Bode plot response, you will see that near the natural frequency and driving frequency you have 2 sharp peaks. Otherwise rest of the area, the frequency is not affected much. Okay. So yeah, flight dynamics is a course where everything comes together. Then yeah, should I talk about the coupling mode? So actually you will see that if you wanted to, let me also talk about coupling, because the next topic that will take up is the spiral mode. So KR, if you calculate for this target one, I think it comes out to be 0.135. Also, please don't be scared if the numbers don't exactly match, because I did the math at 3 am, so it might not be exactly accurate. But yeah, the concepts are still the same, so just be cautious. So what happens, like when the aircraft yaws to the right? That is means your R is positive and we want to stop it. Do you need a negative yawing moment or a positive yawing moment? Negative. Excellent. Now what did I give you? N delta R is negative. Okay. And then KR is also negative. R is positive, which means the yawing moment that I am getting is positive. So I'm good. My aircraft ran this way and then I'm getting yawing moment. It's getting this. Yeah. Okay. Actually, let's move on to the spiral mode first. Let's do spiral mode first. So in spiral mode, we have, so this is a non-oscillatory mode. Why? Because its eigenvalues are real and negative. There is no imaginary part. And it can lead to a gradual divergence in the bank angle and the heading both. So using the spiral mode approximation, where lambda spiral is given approximately as L beta NR minus LR N beta. Yes, I was correct. Divided by L beta. So if you have forgotten, go to lecture 16 or 15 and recall how do we approximate this. I don't have the time to cover it here, but yeah. So now it's asking that is the aircraft spirally stable or unstable? So you are simply going to pick up the values that I give you for L beta, NR, LR and N beta, plug it into this. If lambda spiral comes out to be positive, is the system stable in spiral mode? No. If lambda comes out to be 0, it's marginally stable. Okay. And if lambda comes out to be less than 0, it's stable. And obviously there is no way you can get an imaginary part here, because all of these values are real. Okay, calculate the time to double amplitude or time to half the amplitude. So this is like you can try it on your own, to be honest. Like it's basically you will have an exponential increase or an exponential decrease, and you can find out the doubling or halving amplitudes. Now let me talk about, it's a pretty simple and straightforward mode to analyze, because it has only real eigenvalues, there is no oscillation. However, there is a note between coupling and Dutch roll mode. So like look at this, what's happening. Like stability depends on the sign of the numerator, right? And what happens usually? What is L beta? Where did we see L beta earlier? L beta is the change in rolling moment due to change in beta. Remember dihedral? Why do we have dihedral? To stabilize this effect, right? And that is why this is usually negative and it is related to the dihedral. Then recall N beta. What is n beta? N beta was the change in yawing moment due to beta. So yawing moment and change in beta. So this was related to weathercock stability. Okay, and this is usually positive. Then LR is usually positive and N beta NR is also usually positive, which means that what happens is the first term comes out to be positive and the second term usually comes out to be negative, which means that what's happening,
It's gonna be positive. So the whole
right?
is gonna be positive.
Yeah. Now see, after we added the Dutch roll thing, you will find out that after you add the state feedback, NR will become negative. You see, NR is appearing in both Dutch roll mode. Like when you design a stability augmentation system for the Dutch roll mode, what did we find out? That you are going to change Y sub V and N sub R mostly. Not even Y sub V. Actually, N sub R is going to be the one that's going to be directly affected. And what are we doing to N sub R? We are subtracting N delta R times KR. Remember? This is what we are subtracting. Like the B2 K2. What is B2? B2 is N delta R, right? And K2 is the KR coefficient. And we are subtracting them, which means that we are changing NR. So if we are changing NR, we have to be cautious that we are also affecting the spiral mode. So Dutch roll mode and spiral mode are very intimately related via which stability derivative? N sub R. Note this down in your diaries wherever you have. I'll also make a note here. Dutch roll mode and spiral mode. Be cautious when you are editing or designing a stability augmentation system based on damping ratio for the Dutch roll mode. Okay, good. Finally, this brings us to the last question, which is the roll mode. So in roll mode, roll mode characterizes like how quickly the aircraft like reaches a steady roll after the, let's say there was you pitched up, you give an LLR input and the aircraft comes back, right? All of you have been in an aircraft at some point of time, right? Anyone who's not been, it's okay, but try to relate to this experience. Whenever you are trying to land, you are taking off, your aircraft performs some maneuvers. Like, if you are taking off from John Wayne, then you will realize if you go on Google Maps and look at the runway direction, the runway direction actually points in an east-west direction. And what's to the west? It's Pacific Ocean. Obviously, we won't be flying into that. So let's say you took a flight from John Wayne to Oakland. So the aircraft needs to come up and turn to the right, and it has to do it immediately after takeoff. So when the aircraft is making roll maneuvers, do you see it doing this and stabilizing, or do you see it taking a roll maneuver and very smoothly comes back to where it was? It's very smooth, which means that the roll mode is an inherently stable system, okay? And it's more or less very weakly coupled with the other two systems. So that is why we are studying it at the last. And you will also see that the eigenvalue is negative and much less than the other eigenvalues for the spiral mode and the Dutch roll mode, okay? So, and there is only, so since this is like a single eigenvalue system, we only have this equation to worry about. P dot is equals to LPP plus L delta A delta A. So you pick up the eigenvalues, you pick up the values that I provide you for the Navion aircraft, plug it into this, and then you can go ahead and find out the eigenvalues and eigenvectors for this mode. I think that shouldn't be a huge problem, because it is a single order system, so you have just one eigenvalue, right? And that eigenvalue is, it's on the screen. The eigenvalue of the roll mode is on the screen, not the value but the factor. Exactly, it's LP. You take the Laplace transform. You take the Laplace transform of this differential equation. What's going to happen? This is the input, right? And then, so let's take the Laplace transform. So if I take the Laplace transform, I will have S PS equals LP PS plus L delta A S. And what do we have to take to construct the transfer function? Ratio of output to input. Output is PS, input is delta A. So you will see that PS over delta AS comes out to be L delta A divided by S minus LP. What is the only root of the characteristic polynomial? First of all, what is the characteristic polynomial? It's in the denominator, S minus LP. And what is the only root of this characteristic polynomial? LP. So LP is your eigenvalue. From there you can find out, so basically for first order systems the response is usually given as 1 minus e to the power minus lambda t. This is simply the first order response. It's either an exponentially decaying or an exponentially increasing depending upon the eigenvalues, whether it's positive or negative. And why there is no oscillation in a first order system? Because whenever you will have, so for oscillation, what do you need? You need non-zero imaginary parts. And if you have a second order ODE or a second order algebraic equation ax square plus bx plus c equals 0, where a, b, c are all real numbers, if you ever get roots which are complex, they will always occur in pairs. So you will never get like one root is minus 1 minus iota and the other root is minus 3 plus 5 iota. No. If you have complex roots to a real quadratic equation, they are going to be minus 1 plus minus 5 iota, minus 3 plus minus 5 iota. But for a first order system, you only have one eigenvalue, right? And we have all real parts. So it's going to be a real value, either positive or negative. If it is positive, exponentially blows up. If it's negative, exponentially comes down. The next question is, if we were to solve the full 4x4, if we were to solve the full 4x4 lateral characteristic equation, we would find a real root very close to like what you find from this reduced order model. So you have to think that like, why is the 1 degree of freedom approximation so good? Because the coupling of roll to yaw is very poor. Okay. And finally, like, the last one is to design a stability augmentation system so that I can bring down the settling time further down, which can easily be done. So now basically what are you going to do next here? So just I also brought up a SAS question for this because you might see a first order system and be a little confused. So don't be at all, nothing to worry about. All that is happening here is P dot is equals LP P plus, actually not plus anymore, this becomes minus L delta A KPP. So now you have LP minus L delta A KPP. What's the new eigenvalue of my system? LP minus L delta A KP. So let's say right now I have some desired LP, I have some current LP, I wanted to get it to some desired LP. So you just need to equate LP minus L delta A times KP equals the desired LP. The three values LP, current LP, L delta A and the desired LP are given to you. You will get KP from there. Okay. So the concepts of second order dynamics, short period, long period, the coupling between them, where do you design the stability augmentation system in short period dynamics? Why don't we design it based on the 2 degree of freedom approximation for long period? Why short period is the dominant mode? Then in longitudinal modes, you have Dutch roll and spiral, which are very intimately related with respect to n sub r. And then there is the roll mode, which is more or less not so coupled. And then when we have one free state, which is the psi dot state in lateral modes. What else? Yeah, I think that's primarily all. and designing a stability augmentation system for second order and first order systems. So after I go home, I'll publish the questions on Canvas. I'll upload both the videos on YouTube, and I'll also upload the stability derivatives, but it will be muted one. So if you can follow that muted video, like at least the writing, you can make sense of it. But I'll try to put in its audio later sometime. Okay. So that will be all. If anyone has any questions, yes.
You're having office hours tomorrow?
Tomorrow?
Oh, Monday.
Monday, yes, 2 to 5 p.m.
Okay.
In your lab?
Yeah, in my lab in 134B. So I'll be at my desk in 134B from 2 to 5 p.m. Drop in.
4B is what building?
ELF 134B is Engineering Laboratory Facility. So just in case nobody knows, this is your MDEA, which is your McDonnell Douglas Auditorium. This is your engineering quad. You head here, you will see this one-story building with red chimneys. That's ELF. Okay. Yes.
For like longitudinal motion, you mentioned that typically we design the SAS around the short grid.
Yeah.
Grid. So for lateral, does that same thing apply? Is there like a particular mode we want to design the SAS around?
Yeah. So now the thing is that for example, that's what we discussed. So like in lateral mode, if you wanted to design a stability augmentation system for, let's say, the Dutch roll mode, you have to keep in mind that the spiral mode will get affected. And if the spiral mode is getting affected, you have to then again, take the feedback that, okay, the spiral mode gets this much affected, so I need to correct it in my Dutch mode. So if I try to change my spiral mode, it's going to affect my Dutch mode. And if I affect my Dutch mode, it's going to cause a problem with my spiral mode. So you really can't design a stability augmentation system just keeping one in mind until unless the question explicitly asks you to do so, which a straightforward question does. So if you open a textbook might ask you to design an SAS for a Dutch roll mode. But at the same time, remember that you're also changing the spiral mode characteristics, even though the question is not asking you to look at it. So some question might ask you that, we didn't ask you to study the spiral mode, but do you think the spiral mode gets altered? You have to say, yes, it obviously gets altered because NR is a critical value in spiral mode. Okay.
On the test, if you asked us to do like a SAS around the Dutch roll, do you expect us to also be comparing the...
Until unless the question explicitly asks you to, you don't have to.
Okay.
Yeah.
And you said that the roll is pretty decoupled.
Yeah, roll is like a single order DOF, pretty decoupled from the other ones. So yeah, I mean, you can see that it doesn't like neither R, neither beta, neither psi shows up. It's only P and the delta A. Actually, this is not even an approximation. If you go there and look at it, the other two terms are anyways negligible. Like you will look at the Navion aircraft data that I published today. I have classified some stability derivatives as you can assume them as negligible. For example, X sub Q. The forward force does not change with pitching rate at all. Like it changes. You can go ahead and derive that stability. You can get a very complex expression for